Okay. Let me give some details about the numerical issues in doing embody simulations, in particular related to the ¿Aquí se escucha mejor? ¿Sí? Bien. So, well, this is a sorry. ¿Me escuchas?
Sí. Un poco más.
Okay, so this is a quick review of the meaning of numerical physics or computational physics, in which we have several steps as a scheme to do simulations. In particular, we have the definition of the problem, the proposal of the models, simulation, well, specific schemes to do the simulations, in particular the SPH, for example, to simulate the various parts of the systems. We have real phenomena, we have the theories, the physical laws, the models that come from the theories. We have mathematical models, the differential equation, integral equation, and so on. The physical models, numerical models, because they are not the same, and we have to implement the model, the method, make the numerical implementation and validation. It's just the general scheme. And the steps is programming, algorithms, execution of running of the codes, and the data processing, analysis, and the particular problems we have. So in the case of the embody problem, we have that in general a potential, an interactive potential has two parts, the repulsion part or region in the potential and the attractive part. So the competition between these two characteristics of the interactive part potential and the kinetic energy is what established the structure of the system. Then we have in general that we have to solve n equation for each of the bodies, and we have the problem, the general problems of the general ingredients to the n-body problem. We have to have a lot of bodies. The bodies have to interact between them. How many bodies are necessary to have a problem, and so on. This is just a historical review of the status. So this is a very old simulations that try to reproduce at least morphologically some of the interacting galaxies. We have here the antenna, we have here the mice, and this is the question we have to solve in the case of cosmology. We have here the expansion of the universe. We have the Newton law here, and this comes from the background. And we can introduce here a special function to include some specific models that we can to try instead of the usual one. For example, a Yukawa. So we have two particles that are interacting. We have to solve this problem, and we have the simulation box. We put a lot of particles. We compute the interaction between them, and this is the general scheme to program to make it more or less explicit. We have initial condition. We compute the force between the particles. We have to do this n squared if we have, in this case, particle. We have the advance or evolution of the system using the Newtonian law. In particular, you use leapfrog, and we have the data, the output of the data, and repeat the process as many times as we want or we need. There are in this case, three numerical parameters. A galaxy, for example, consists of 10 to the 10 or 10 to the 11 or 10 to the 12 solar masses. And in the biggest simulation that we have, at least these days or these years, we have 10 to the 10 to the 12, no, 10 to the 10 particles, or the computer can deal with this number of particles. We have the step size for the evolution of the system, and we have this parameter which is needed to avoid the divergence of the interacting particles. So if we have two particles very close, we see that the potential is growing fast. For example, if they are in the way to collide. So okay, so we have in particular, so that was the particle method. The particle mesh that was explained by Octavio consists in given a certain distribution of particles in the space, we create a mesh or a grid, and in each point of the grid we compute the density. For example, this point in the grid is labeled by I and J, and we have to compute, given the distribution of particles in the space, we have to compute the value of the density in this point. And we can use interpolation method. Also, given a kernel that give us information, for example, if we want to compute the density here, and if we have a particle here with a mass or with a certain density associated to this particle, so if the distance is larger than this point, so this contribution to this sum is very low, but nearest particle contribute a lot. So this is a kind of a Gaussian, for example, or a spline, or some particular methods, definition for the kernel. Another method is do the same thing as before, but for particles that are close to the particle we are trying to compute the force, we have to do the direct method. It means particles around this, the red one, we use just the particle method, and for the particles that are at great distance, we use the mesh or the grid method, for example. In the case of the tree code, we have the following. What we have is that particles that are together in a certain volume with a certain length, this volume, and we have the distance to the center of mass, for example, that is R, we apply this condition. If R is bigger than L over theta, theta is a numerical parameter, then we have that this volume contribute to the force as a expansion, using the expansion for the potential, no? That we saw yesterday. So, but if we are closed, then we go inside of the cell or the volume and try to see if the smaller cells that we can build here satisfy this condition again. For example, if theta is equal to 0, this condition never will satisfy, right? And so we have to zoom for all particles, and we recover the particle-particle method. But if theta, for example, is bigger, this condition can be satisfied more or less frequently. And then we can use the multipolar expansion for the box, computing the mass, the quadrupole momentum, the octupole momentum, depending on the approximation. Now, the difference between the tree code and the particle mesh or grid is the following. When the system is very uniform, like in the beginning of a cosmological simulation, set equal to 1,000 or 100, for example, we have that the distribution of matter is very uniform. So in this case, the mesh, the grid, is very efficient if we use, for example, the Fourier transform to solve given that rho is very uniform, then using the fast Fourier transform we can find very rapidly the potential. But for set values close to 0, I mean around 10 or 5, for example, we have that the particles are clustering. So in this case, the tree code is more efficient. And for this, we can test some when using the numerical code, for example. Okay, so what is the meaning of what is known as numerical relaxation? If we have a particle, then given by delta, is a particle in the origin, for example, or some point in the space, the solution is this, for the potential is this one, right? So when two particles close together in the simulation, what we have is before two particles, they close together, and given that this potential is growing very fast as a function of the distance, then there is a certain kind of collision, like in gas, right? So for a star or for dark matter particles, this is the Boltzmann equation, collisionless. There is no collisional term. But in the simulation, we have that particles can be close together. So instead of solving this Blasov equation, we are somehow solving this equation, the hydrodynamic equation, right? So they are, in fact, artificially are colliding the particles. So this is a problem. Then, what we have to do is, collision is the mechanism that a system have to erase fluctuation. And in English is iron the fluctuation, right? That's why I put an old iron machine to erase the. But this is artificial, right? This is a very artificial result of the simulation because we are implementing this potential. So this is a problem, and it's called numerical relaxation. How can we solve it? As we have a lot of particles in the real case, and we have not all the computational resources to deal with this simulation, many particles, many real stars or many real dark matter particles are considered as a one particle. in the simulation. So all these particles, for example, for the omega cluster, it has 1,000 stars, right? No, 1,000,000 stars. And if we are using a simulation with n equal to 4,000 particles, then each particle is represented like 100, for example, or 1,000. So 1,000 particles is real is corresponding to one simulation particles. Okay, so the problem is that if we use this the real potential, the real Newtonian potential, we have this problem. Okay, so if this is a virtual particle, but inside inside there are many stars or many dark matter particles, so a particle should interact with the potential that comes from this distribution. And this distribution, for example, for the more usual distribution for like a star cluster, for example, is the Plummer model. So if this cluster particle is well represented by this distribution, this density profile put it here give us this potential. So we have that this particle is not interacting with one of each of these one. It's interacting with all the cluster. So then with this parameter, we're avoiding the relaxation problem. That's the main point. This is the concept. Okay. Next, what we have to do when designing the code? Consistency, convergence, and stability. Consistency means that we can reproduce a typical solution. Convergence, when I increase the number of bodies, I'm going to be more close to the real case. Stability has to do with, for example, the leapfrog. The leapfrog is a very good method, it's symplectic, as Octavio told. But the leapfrog is unconditionally unstable. So if there is a small error in building the initial condition, this error will be propagated in the simulation if we repeat this code a lot of times. So the leapfrog is unconditionally unstable. So always there is a numerical solution that will grow as we advance the simulation. What we have to have at hand to see or to check that our simulation is going well: conservation of energy, linear momentum, angular momentum, and conservation of the volume in the phase space. Okay, another point. This is the classical physics, and the main point here is the virial theorem. This is the virial function, is the force dot with the position. We average in time, and we call this quantity this G, for example. It means G is equal to the final of this one. Okay, when we evolve the system for a long time, this goes to zero. It means that when t goes to infinity, somehow this function will repeat itself. So we have that the average of the kinetic energy multiplied by 2 plus the virial average will be 0. If the potential is of this form, proportional to r to the n plus 1, then we have that the average will be in this way. If n is, as in the Newtonian case, we will have this one, if n is equal to -2. But the model we use is this one. So we won't have will not satisfy the visual relationship if we have a numerical parameter here. So when epsilon goes to 0, we will approach into the visual result. Okay, this is more details about the tree code. The main point is how to build the cells where we have put in particles. So this initial box contain all the particles. Then we divide in the two-dimensional case in 4 small boxes and see how many particles we have in each one. When we have a cell with only one particle, we stop here. We stop there. And when a cell doesn't have particles, we simply don't consider that cell. Erase the cell. And repeat this step until we have cell with one particle, and so on and so on and so on. So this is the root. The root is all the box that contain all the particles. Then the daughters or the sons, and so on and so on and so on. So if we want to compute the force in this particle, if we satisfy this condition for this cell, for example, we go inside and divide the cell, and we have this case, right? And so on and so on and so on. That's the method. Okay, this is what we see yesterday. Also this one, as we see the, okay. So we need to compute the force using the tree method. So we start erase or clearing well, we start with a particle. We start with this particle, for example, right? Okay, so we have its position, and we clear the potential, its potential, and clear its acceleration. Then we walk the tree, and we start with the big box. So we want to compute the force here and the potential here due to all the particles. So we are in the whole box. So obviously satisfy this condition. So I have to divide in 4 small boxes, right? And ask if this condition is satisfied for this one. If not, we will go inside. If, for example, for this one, if this small box that contains 2 particles is very far away from this one, so we just need to compute, for example, the momentum, the mass of the total cell and the quadrupole momentum, and that's it. Okay, so that's the meaning of the tree walk. Start with a bigger box with a certain size, and given the position of the particle, we are trying to compute the force and the potential, and walk the tree. At the end of this walking, we have the potential, the total potential, and the total acceleration due to all the particles. And what is inside this walking the tree? Okay. We ask a question if we have to update this particle. Normally is always true, so we go from this one. If the particles are the same, so we do nothing. And if the particle is different, or the particle and the cell is different, we ask the next question: is the particle is a cell, or is the particle is a body? If it is not a cell, it's a body, and then I zoom. If it is a cell, I ask for the condition is here, and if the condition is satisfied, I just use the quadrupole momentum and the mass of the cell and compute the forces, the two terms for the forces. If it is not satisfy the condition, then we go one level deep and repeat the same. You see the normal walk tree here is the same instruction. Normal walk tree the same, but instead of the root, the initial box, we have the next level, the boxes in the next level. So this is a recursive method. Okay. So we saw this yesterday, and okay. Okay, this is an important point: the complexity of the numerical code. And normally we use this notation, the big O notation. If something is of the order of 1, is that just one operation is done. And if we have a lot of operations that depend on the number of particles or the number of equations, we have that the order of the computation or the complexity of the computation is like O to the O of n, or like the tree code is like well, this is a question, like n log n, for example, or Fourier is more or less O of the order of n. So how we can understand this concept? Imagine that this is better explained in this one. If we have a task that depends of the number involved as a square and as a power of 1, n squared n, and a constant, then if we increase the value of n, for small values of n, these two terms will be very similar in size, the 3, 1. But when n is increasing, making bigger and bigger and bigger, then the difference between these two terms is begin to be dominated by by this one. For example, 3n squared, when n is equal to 10, we have that all the computation is given by around 73%. The next term, 10 times n, will be taking 24%, for example, and the constant will take 2.4%. And when we have n equal to 100, then we have that the first term is dominating, and then it takes a lot, or mostly the resources, 96%. So this is the way to compute the complexity of the code. So and a question is for the 3 methods, why the people say that the complexity is n log n. Okay. Okay, let us do some, go to the computer. So let us review what we have done. Okay, so I hope we expect that all you have reached this point, the 6 steps in the first install file, making the simulation that we can make the 2 spheres and making collide. I assume that The next is installing another simple code, the embody tree, which is using the tree code. We follow the same pattern. Remember, everything is done like this one.
This is for Linux.
It doesn't matter in this case because you already install everything in the first installation file.
Okay.
Mm-hmm.
Can you repeat the instructions?
Just it's repeating the pattern. Make -f NAC body install and the name of the code. Mm-hmm.
So that's not in the installation for Linux, right? Those implements.
For what?
If your code you when you play is not displayed in the installation for Linux.
It's the same.
No, no, I said.
Yeah, but in the file you give us, that code doesn't come with version. It's just for the OS X.
En las instrucciones no está.
Yeah,
For Ubuntu.
yeah, for Ubuntu.
Yeah. Yeah, but it's the same. The problem between Ubuntu and Mac is installing plplot and that. But the codes that don't need visualization is the same.
What did you write there?
Huh?
Make -r, NACBody, PKJ. NACBody.
Do that.
So,
Just leave it.
yeah, you just do in the NAC body folder. It doesn't matter if you are in Ubuntu or in Mac. It's the same. The difference between those systems is just the plplot and that's because there are some issues in. Maybe for the guys we are not installing or don't have a running the visualization package. Maybe it's because Xquartz is not running. But you always can do the following, I think. We just pick. Let me open in Xquartz on the terminal, and maybe here we'll be running the programs because this is just a terminal in X window. Mm-hmm.
I don't have
What?
error. I try to make the make myself. Oh, but that's in the Mac OS.
Yeah. But after the first step, the next are the same.
That's what I did here.
So we have to do that.
No, this is just for the guys who are using Mac and Xquartz is not working. So I open a terminal in Xquartz and then I just use the.
Is there a way to use Xquartz without opening the terminal from Xquartz because it has like some drawbacks, like you cannot paste things.
No?
So you have a few lines of code and then you cannot paste them. You have to.
Okay.
So is there a way to use it directly with the Mac terminal?
Yeah. As
Because when I try it, it says that plplot doesn't work if I don't use the Xquartz terminal.
You mean when you use a normal terminal like
Yes.
this? Like this one, for example. This is a normal terminal.
Yeah. Can
Yeah?
you just type again and plot2d? that wouldn't work.
In your case, is it not possible to open a display or something like that?
This display is not opening because it says that.
But Xquartz is working?
I can do it while I use the Xquartz terminal, but I cannot do it without what.
I don't know.
I think it's more of a particular doubt, so it may be.
But it's work here.
Yeah, there it works perfectly.
Okay.
But in the other terminal it doesn't work.
Yeah, and this is a bash also. My, no.
A more particular question, maybe we can sort it out in the break or something.
Okay. So we were here. What else? Okay. But let's try it. So. So I make a lot of directories in Borramed because every code writes something, and sometimes we will have a mesh in the directory. Right? So. So, for example, let us make a model.
They sit on the neck.
Everybody does the make, the embody tree.
Because that's new in the Dropbox, right?
Yeah, sure. And let us. Okay, let me. Okay, the first thing is go to the home, and then remember that I put the package here. I erased them, okay. But in any way, it's in Dropbox. MN. Codes. Okay. This is the Dropbox. So. tar xbf and receive and embody tree. So with this open the, unpack the embody tree, and then you have all the sources available, and you can make then then produce the binary. Well, in this case was already done, but we can clean and then install the body. So you have to unpackage from the files in the Dropbox and then go inside the NACBody directory and make the.
Just 1 second to do that.
Fabio, do you do it?
And body tree.
Yes.
Okay.
Yeah.
Okay. So let us test it. So here we are. We make a sphere with 2000 bodies. And then run embody n2 with initial file equal to a sphere. Okay, but the main thing to do is time and the instruction before. And the time is the first value, this one. And then let us try the tree method. And apparently is bigger the time, but let us make a bigger sphere. And repeat the process. The embodied N2, which is PP or direct method, is slowed down very. So we have 12. And if we use the embodied tree, no? Do you notice the difference? Because one is the complexity is n squared and the other is n log n. Just increase the number of particles, for example, to 8, and let us see how many seconds or minutes time lasts this embody n2. And then for the question why the tree code is O of the order of n log n, you can just do this testing, increasing the number of particles and plotting in log, right?
Can you show the previous slides? I can use the
Yeah. Let us let the code finish, please. Yeah, 47. Okay, the history is here. So we use model to generate the sphere, the initial condition, use embody n2 with this initial condition, and we tested, instead of this we use time to report the time.
And the make,
What make?
the make tree.
No, make is not here. Making the The sphere?
No, the embodied tree.
No, this is another terminal.
Okay.
They are different terminals.
Just give it for a moment.
So this terminal is for where I make the binary. And in another terminal I tested the code, just to not mesh. Okay? Okay. So let us try the tree. Well, we lost, well, it was like 47 or something. Check that it was 4 and the other was 47 or something like that. So the difference is becoming important when the number of bodies is increasing. Okay, so we can make more particles. Instead, this 16, for example, and then repeating the process just to test how many times the M-body N2 spend doing this simulation. But you can see that it's suffering, right? Are you doing this? Do you have problem? No? Irvin? No?
Which error bars do we have to have on the conservation, energy conservation?
You mean in the fluctuation in the... Okay, in this case these are very tuned to work well. The parameter epsilon is chosen like the best one for this kind of simulation for star clusters, and the time step is also good, but you can vary the epsilon and vary the dt, the time step, and to see how it's changing the size of the fluctuations. Okay, let us interrupt here. Around 1, right? And let us try the... Okay, that's it. So, 6 instead of 100, or I don't remember. And then we have also, let us make a model with less particles. So the energy is here. So the total energy is here, is the column 3. That's the fluctuation, but let us put it in another format. Yes. So this is the fluctuation here. So the error is very small, right? And it keeps.
That's the error in the energy, right?
Huh?
That's the error in the energy, right?
No, it's the total energy, but it's fluctuating. It's fluctuating.
¿Qué tanto tiempo ocupas?
¿Manda?
¿Qué tanto tiempo?
¿Cuánto falta?
Pues en principio tienes 5 o 10 minutos más.
Okay. And this is the kinetic energy, the total energy, and the potential energy. Any question? Yes?
If I check the graph,
If you work?
say the graph, like, how can I do that?
Sorry.
How to design the graph?
La quiere guardar.
Ah.
the configuration?
I don't remember. uh, You have to define the device as a PDF or EPS or something like that. But let me see where is.
Well, but the animation is also like, can you take a video of the
Yeah.
animation also?
This was produced with the
Oh, it's simple.
the same code. Well, analysis graph instead of mplot. So I just save as a EPS, for example, each image, and then collect all the frames and with QuickTime or something like that, put all together.
Mario, is there a way to plot in 3D these things?
I did it a long time, but I forget about 3D.
But it's possible.
Yeah. Okay. Let me. So this is a lot of examples. All this graph was done with this mplot 2D. This is a Gaussian halo. This is a Lennard-Jones halo, like a drop in the empty space. This is a scalar field also. This is a galaxy simulation, building the initial condition and then making the disk evolve without halo, and you can see how is fragmenting the disk. And when use an halo surrounding the disk, we have that there is no clustering, and somehow is viralize the disk or establish the structure of the spiral arms and something like that. But here is including the halo, but the halo is not displaying, but is there in the simulation. This also to build the initial conditions, also to do these schemes, and also this is from Ruslan, the first simulation that Ruslan did. We have and this is very important. Let me try it again. Just check the two disks. H1 is colliding head on, and then the code is losing momentum, angular momentum. That's why one of the disks is going outside, right? So this is a problem. This was done with gadget 1, and gadget 1 had in those times had this problem of losing angular momentum. But this was placed in the XY plane to hit head on. And this one was done with this n-body 3 code, and you can see that the angular momentum is very well conserved. So this is a test to check angular momentum in this case. This is the disk. This is the disk seeing H on. This is the bulge, and this is the halo. This is the same, more or less the same, but just seeing the disk and you can see how it established the bridge between the two galaxies. And then here something happened, and we analyze this galaxy. Just we observe from the center of mass of this galaxy what is happening, and what is happening is this. This is that galaxy. Occurs the collision, perturbs the galaxy, and then establish the spiral arms again. And you can see that the spiral arms are changing from trailing to leading, and appear this particular phenomenon. The arms are changing from leading to trailing, and to understand more or less this behavior, we can analyze the disk in spherical rings and compute in each ring more or less at this place where the spirals arms are, and see how is is changing. And you can see that the tangential acceleration is changing. That's why it's changing from leading to trailing. Okay, and this is 3D, as Jorge asked. But I leave it. I not continue to do 3D. So this is the simulation Alma did. Just put in a box randomly in the box 100,000 particles, and I think this Alma did with this very popular visualization package. Is ¿no te acuerdas, Alejandro? Pop, right? No. Anyway. And this is mine. Because Alma doesn't want to share the code with me. Okay, so that's the reason I started to do my own codes. There's another one, and so on. And we can analyze each halo, looking for the density profiles or the rotational velocities and so on. And this is with the scalar tensor theory also. And this is the power spectra of that cases, varying the parameters of this is the standard model, evolving from set and set. This is the scalar, including the scalar field, lambda CDM, scalar field with 2 parameters, or with the scalar field with another parameters, and so on, and how it is compared with observation. All this graph was done with the mplot2D. And this is the gravitational collapse. That is a homework for you, which I think Octavio write this project for you. And it's a isothermal sphere that is rotating with 2 perturbations at the initial time in the equator plane. So you can study this isothermal collapse and try to understand the stellar formation, for example. The numerical problem really is that the density here is growing very fast, from I think 10 or 12 orders of magnitude. So this is the problem. Any questions? Gustavo, it's time to go to lunch? So, and Jorge? Yes?
Is that project itself a star collapse?
Yeah, it's the isothermal collapse. It's a very standard problem. Any other question, or it's time to go to lunch? Lunch, okay. So everybody, most of you install plplot, the library, or there is someone is or couldn't install the library. Okay, so we finish here.